Thanks a lot. I'm going to talk to you about a collaborative project that I'm very excited about that's funded by the U.S. Forest Service, Pacific Southwest Research Station, CAL FIRE Greenhouse Gas Reduction Fund, and the Marin Municipal Water District. This is a conference about redwoods, so I need to give you a little bit of context about why I'm talking about a disease that primarily affects oak and tan oak. Sudden oak death is an invasive emergent disease that affects many forest types within California and Oregon, including redwood forests, and it's particularly devastating to oak and tan oak. It's caused by this organism, Phytophthora ramorum. This is an oomycete that includes a lot of other destructive Phytophthora that you might know, Phytophthora cinnamomi, Phytophthora lateralis, as well as a bunch of other pythiums that cause damping off. They're major pathogens both for forests and for agriculture. This pathogen was introduced to California sometime in the 90s from an unknown native range, and it emerged as a major cause of disease, as I said, in many forest types that include oak and tan oak. I want to give you a little bit of background about the disease and give you the context of why we're talking about it in reference to redwood forests. There are a few key hosts that I need to highlight. They're the hosts that cause the disease, that drive the disease to spread across the landscape as well as its emergence. Some of these you may know about, such as California bay laurel. This is the host or native tree that is the most competent, meaning that it is the most potent sporulation source within the landscape and within stands. An important thing about bay laurel is that even though it supports a lot of sporulation, it's very susceptible. It does not suffer any mortality or any immeasurable negative effects on its health. So people say that it's the typhoid Mary of this disease. It's good at spreading it. Our most problematic species is tan oak, and that's because it both is able to spread the disease, support sporulation, and it develops a boll canker, which eventually girdles the tree and kills it. That happens pretty quickly after the disease or the pathogen gets established and weakens the tree. A number of other more minor pests and pathogens, such as Armillaria, Hypoxylon, and ambrosia beetles, will emerge and then finish off the tree. So you notice those a lot on diseased trees. The disease is named for oak. Of course, tan oak is not an oak, but I do want to point out that coast live oak in particular it also suffers a lot of mortality from this disease. However, there is no oak-to-oak transmission. So all boll cankers, whether they're on tan oak or on oak, are dead-end infections for this pathogen. Pathogen gets in there, it'll kill the trees, but it will not spread from those infections. So that means that if you have a stand of pure oak, you have a good situation, pure oak, coast live oak, and no bay laurel, there's no means for transmission from one host to another, and the disease shouldn't be an issue in those stands. Of course, if it's all tan oak, it's a different story because you have the transmission pathway. And of course, I also want to point out the redwood is a susceptible species. Those of you that know some things about this disease may know that redwood is susceptible. It's not a very competent host in terms of sporulation, and the disease, the pathogen will infect needles. It'll kill needles here and there, but it's really not that big of a deal on a species level. Redwood is even that important in terms of supporting the spread of the disease. But what we were talking about here, and the reason that I wanted to come today and talk to you about this disease is because it is an issue at the level of the redwood ecosystem. It causes a lot of damage and degradation of forest health at the whole ecosystem scale. Some of those effects include interactions with fire. Margaret Metz a few years ago in a body of papers showed that the fuels that are generated by this disease can increase mortality that occurs during fire, including increasing mortality of redwood. So larger trees or medium-sized trees that otherwise would survive the fire are killed during the fire, presumably because the root systems are damaged. More recently, we've also shown that increased accumulation of fuels also leads to increased loss of soil carbon, soil nitrogen, soil phosphorus, calcium, and changes in soil pH during fire as well. So there are interactions, there's second order or third order interactions that, ways that the disease affects redwood ecosystems. Something else that's important to point out is that this pathogen is now well established within California, meaning that forests, redwood forests that have a tannoy component, whether they have been infected for a long time, up to 2 decades, or have not been invaded, are at risk, and then eventually this is an issue that most managers are going to have to address in their redwood forests. If you have a tannoy component, you're probably eventually going to have disease. This was a modeling study. It was a culmination of a number of efforts, modeling efforts, and we showed that it's really too late to eradicate the disease at the statewide scale, and that we need to move on to mitigation strategy. Even though we point this out in the paper, the reaction to that particular publication was really focused on that the eradication was no longer possible, and it was actually very difficult to direct the press. We got a lot of attention on this, and it was difficult to direct the press and the public to what happens now, which most of my work has focused on. The funny thing about this study is that one of the reviews that we got back said, okay, this is a great study, your high-level modeling and stuff, and it's all seems good. But what's surprising about this? Scientists have known that this pathogen could not be eradicated for some time. And we said, oh yeah, well, we know that too, but it is time to shift focus to more mitigation. And the reaction to this paper was interesting because the public didn't realize that eradication was no longer possible. And so there was a lot of attention, and it was difficult to get the focus back onto forests like this, which you probably know about, whether it's in the context of redwood or not. Areas that have very high density of tan oak, post-harvest stands that did not get the kind of silvicultural attention that was needed to regenerate Douglas fir or redwood. These are very dense stands. There's a lot of this out there. There are problems for many reasons, including the potential spread of disease. This study is focused on mitigation in highly impacted stands, and this is a photograph from Mount Tamalpais in Marin County, the location of our study. And in this area, also a stand that had a lot of historical logging regenerated. This is a redwood forest, even though it was dominated by tan oak. The disease has been present in this stand for about 2 decades, and what you're seeing here is mortality of the overstory, but dense regeneration of tan oak. And that's a characteristic of this disease. It infects above ground tissues, so it does not necessarily kill the individual. And as you know from, you've probably seen this in areas, if you go in and you cut down tan oak without herbicide or some other treatment, you'll get dense tan oak resprouting. The same thing happens with this disease. When the above ground biomass is killed, there's prolific resprouting, and you get a condition like this. This is a redwood forest with a very dense understory tan oak component. This is what it looks like when you're inside of it. It's difficult to photograph and not very interesting. The pathogen is still present. It kills these sprouts, but they continue to resprout, and we don't know how long that will be maintained. And that's our problem here. It's limiting redwood regeneration, And that is a goal of the agency, of the Marin Municipal Water District, which sponsored this work. Restoring these stands, they're problematic for a lot of reasons. They have a lot of fuel. Their goal is to have overstory redwood, and we set out to test to see if we could do that. This is a part of our study on Bolinas Ridge. We have 3 study sites that are included in this. The design of the study is a set of blocks of 5 1-acre plots. This includes plots that were in red that were randomly selected as controls, and then we randomly applied a number of treatments on the remaining plots. Our goals here are to increase growth and dominance of redwood. Our aim is to increase carbon sequestration in these forests. We think that we've got a pretty good chance of doing that as long as we can get redwood established and get the tan oak out from the understory. The other benefit of this is that not all tan oak have died, so there are many residual overstory tan oak trees, and reducing tan oak density based on our epidemiological modeling suggests that that should protect those trees over the longer term by reducing sporulation loads. This is a water district. Its mission is to provide water to millions of people who live on the peninsula. So we are also measuring water and aiming to increase or maintain water provisioning. And there also is, we are also aiming to reduce fuels, both the tan oak density as well as ground fuels. It's Bolinas Ridge. We have another site that we did this on, total of 30 acres, and this includes redwood and a mixed evergreen forest, which is Douglas fir and tan oak. Okay, this is the equipment that we used, an excavator with a masticating head. One of the primary treatments was mastication. We also had 2 of these skid steers. These are equipment that is owned and operated by the water district. In some areas that were too steep, we had to do a modified mastication where we needed hand crews to actually do the work of cutting down the trees. These were piled up, and then the masticator drove over it and masticated it in place, and that stuff was spread out throughout the area. I've already shown you this photo, but I just want to point out now that what you're seeing here is the transition of the treated area, which is in the foreground, and the untreated area, which is there on the right. It did make a big difference very quickly in these areas. And one of the nicer things was that once you remove all the tan oak, you realize that it really is a redwood forest. That's hard when you're in that sea of tan oak to really understand. But there is redwood there. And so there is the capacity here for increasing redwood dominance within the stand, and also increasing growth of residual trees. And we hope that will happen. Here's a photograph of what there's also areas that were too steep. We had to use a hand crew and pile tan oak materials, and half of these were we randomly selected for burning of a pile. So there's a fire component too. Okay, our measurements are, we measured water outflow. As I said, it's a water district that's important. We're measuring greenhouse gas dynamics, carbon dioxide, that's soil respiration, methane flux, and nitrous oxide dynamics. And we're also measuring changes in productivity. Immediately, what's happening right now is measuring root and litter turnover. That's a lot of work, but the reason that you do it is because it's a sensitive measurement, and it can tell you if you're increasing productivity on the short term. What we really want to know is whether we're getting more wood into those residual trees, as well as if we're getting regeneration of redwood. But that takes longer to be able to measure. So we're doing multiple things here. We're also measuring shifts in biomass distribution. So let's look at some results. Here are our set of treatments. Basal area was more or less uniform across our treatments prior to doing the mastication and piling. And then afterwards, because we removed a lot of small trees, but they're very small, and all the redwood were left. The reduction in basal area was pretty minimal. Occasionally some dead snags and other things were knocked down in the course of the treatment, and that's why the basal area comes down a little bit. But there were no significant changes here. Stem density, very high within these stands initially, and the treatments greatly reduced that, and it didn't matter whether it was a hand crew or the different mastication treatments. If you go out and you do this kind of removal of small trees, the crews are good at it. So you can go out and do something that's effective in terms of reducing density. Here are some other things. Like I said, one of our goals is to reduce fuel levels. Our mastication treatment had the immediate significant effect on that. And I think that's because it was more consistent in terms of the equipment moving around and distributing the material more evenly across the sites. And what we found in terms of forest floor mass, we added a lot of material to the forest floor. In particular, in our mastication, our modified mastication treatment, where stuff was masticated in big piles and then moved around, that was less uniform. So we had areas where we had a lot more accumulation of those masticated materials. Here are our preliminary results of the greenhouse gas dynamics, and what we found is that at least so far, we just started these measurements in July, but what we've seen so far is that the rates are higher in the masticated treatments, which makes sense to me because there's a lot more material there potentially for decomposition. And what we don't know when you measure soil respiration is what component of this is decomposition versus what component is respiration from living roots, so which would potentially indicate an increase in growth. All we know here is that the total amount of respiration is higher within these stands, and our aim is to do this. Is very preliminary. We have the treatments established, and our goal here is to measure this for 3 years so we can understand if we achieved our aims. A few other things just to note. We found that these sites are consuming methane. The soils so far are consuming methane. That's interesting because ambient methane levels are extremely low in this area. The air quality is very high. There's a benefit there. I don't know if anyone else has measured methane dynamics very much in redwood forest, but the bacteria in these soils are consuming methane, and they're consuming it more rapidly than in comparison to other types of forests. This project also includes measurements in the Tahoe Basin, and the rates of consumption are higher there. We also were effective in increasing moisture content in the soils in these treatments. Basically what you're seeing here is an immediate wet up of the soils and the onset of winter rains, and then soil moisture is consistently higher over the rest of the growing season. We're optimistic that will help increase growth of residual trees. That's something that we're going to continue to measure. The other things that you do with this are to estimate how much of the water precipitation is being stored in the soil versus outflowing potentially down into the reservoirs. And that's what comes next. That's just a photograph of one of the sites. And the last thing that I need to point out to you is this is expensive. These are difficult areas to work in. The disease has greatly degraded these areas. So there is a very high cost of treating these areas. And what's unclear at this point is where we should be applying these funds, because they are dense, it is expensive. Should we be focusing on these stands, focusing on stands that have lower impacts, or potentially focusing on areas that have that have not yet been invaded, but where we can avoid these impacts. So thanks. Thank you very much.
Time for one quick question. Why is it doing that?
Are you doing any planting or anything to kind of get more of that or harvest?
Yes, are we doing any planting? The biggest problem with, we have the capacity, the flexibility to do planting. We want to do that, and what we haven't been able to figure out right now is what we should be planting. Also, because the initial experiments were the treatments were expensive, we also have to weigh that as well.
Thank you.
Any other questions? I see Richard Cobb, Dr. Richard Cobb still here, and for those of you who weren't here, he spoke about a study on sudden oak death in Mount Tam, and I had a question for him, that no one else has a question. I was wondering if you interplanted, he was really looking at increasing redwood growth where sudden oak death and very excessive tan oak site occupancy had occurred after sudden oak death killed those trees. And I was wondering if you interplanted redwood to increase the site occupancy of conifer. And I had a second question related to the burning of slash piles on the steeper slopes by the hand crews and whether there are any piles left or if you had problems with the burn getting away from you.
Yeah. Those are great questions. I appreciate it. We have talked a lot about doing planting and planting redwood. The water district, Marin Municipal Water District, would prefer not to plant Douglas fir because, like many places, there is a problem of Douglas fir invasion into mixed woodland communities, and given the effort put in restoring oak woodlands, it would be ideally we would be growing redwood within those stands. At this moment, we have not planted anything. We have the experimental capacity to do so. The emphasis has been on getting the treatments completed and then beginning the measurements. And it's kind of it's an evolving experiment. Of course, our aim is to reestablish more redwood within those stands, and so planting may be necessary. If we do so, we will do it in a stratified random way on top of the other treatments that we've done, both the piles, some of the areas have piles, some of the areas we have randomly applied burning of those piles, yeah, we would stratify the planting on top of that. I've halfway answered your other question, which is about the piles and the pile burning. Any kind of burning is difficult because of the permitting process and the expectations that the burns will not get out of control. So we didn't have any trouble with that because of careful planning by the water district, which was essential to getting any of the piles burned. I think I mentioned this a couple times, but we burned half of the piles. And we did that because we knew we weren't going to be able to get all of the piles burned, and so we then integrated into part of our experiment. We'll burn half of our piles, which is 2 of the 5 blocks. And in the piles were done in 2 of the 5 blocks, and then we burned half of those, and we applied that randomly, which was fairly easy to do. Given all the site preparation with all the mastication that we did, it was perfect conditions to do a broadcast burn, a prescribed burn, but we looked at it, we talked a lot about it, and we recognized that if we went that direction, there was a great risk that we would not be able to get it done. So we went the other direction, burned the piles, did it with the fire crews and an engine on site, and that's why the burning was restricted to the piles. There's a point that some of the people have asked me about the cost of those treatments, and just another point that I would make about it. Why are those mastication treatments so expensive on Mount Tamalpais? That is in great part because of so much public attention to those treatments. There is a lot of time spent moving materials around, covering up tracks of the machinery and so forth that add to the cost of the experiment that would not, to basically get public buy-in, to make the treatments look good. This is a very high-use area, and in order to get public buy-in, the treatments had to look good. And that meant a lot more time for the crews and the machinery. And I'm hopeful that in other places this kind of restoration treatment would not be so expensive. But those are the constraints that we're working with. Yes?
So I've seen how the downtown forest changed the town this fall out.
Yes.
You know, we just took down the homesteads that made it down.
Cool.
So, but one of the things that's occurred to me is that the town is a major source of mass crops, and so what's going to replace that? You showed that 2030 photo, or not photo, but the idea of how far it's going to spread and eliminate canopies throughout the landscape. What are we going to do to replace that function?
Right. So in redwood forests, Tannock is fairly unique. It is in redwood forests that don't have Douglas fir. It's the sole ectomycorrhizal supporting species. So any matsutake and other ectomycorrhizal fungi, we will presumably lose them, or at least their biomass will be reduced. The other problem is that if there is no bay laurel, Tannock is the only nut crop that occurs in redwood forests. And we don't have a suitable species, a true oak species that would grow well in those darker, damper environments. So Tannock is really unique in that it's a hardwood that does well in the conditions of redwood forests. Now, when we talked about replanting and what we would want to restore with, in terms of ecosystem function, it makes a lot of sense to get a tree with a good nut crop in there. But you keep coming back to the key problem is Tannock is the species that's well adapted to redwood conditions. So we're not sure what we can do there.
Have you looked at whether or not chinkapin could fix on that spot?
Chinkapin is a potential, that's a good point. I think that's worth putting into the conversation. It has the recent discovery on Mount Tam is that chinkapin is also susceptible in areas with a lot of inoculum pressure, and so we're not sure if we would be successful with interplanting it.
So you mentioned soil consumption as methane.
Yes.
Factors that affect bacterial consumption of methane.
Methane consumption is oftentimes limited by diffusion of methane into the soil. So soil texture can be an important factor, and also the moisture conditions. So that data is very preliminary. We're encouraged that the soils are consuming methane. They're consuming, and the air quality is very, very good on Mount Tam because there are thousands of miles of ocean between it and the industrial sources. And so what's surprising is when you look at the Tahoe Basin, even though the air quality is lower, and that might sound surprising because the air quality is pretty good in the Tahoe Basin, but you can measure higher ambient levels of methane in the Tahoe Basin. But despite that, the rates of consumption are higher in these more pristine redwood forests. We have to measure this throughout the course of the year, after rain events and so forth, to ensure that to see if those soils are consistently a sink of methane, and whether or not they will shift to sources or if the consumption rates will lower. Because the funny thing about methane is that soil bacterial communities, parts of them consume methane, other communities produce methane, so there's a balance there. But it's encouraging. It hasn't been shown yet.
Thank you.
Sure.